Hi class, this is your digital snow day lecture. Um, Digital day, I guess at first I thought it meant because the temperature is in single digits, and then I thought it meant we're afraid your digits are going to freeze off. Uh, but it turns out we're supposed to have digital classes. So I'll make a couple of videos today and post them up, and hopefully, although we lost a few days, we won't fall too far behind the AP schedule. So this first one is a review of some natural logarithm properties plus some calculus. In class on Tuesday, we defined the natural log function in terms of a definite integral of 1 over x, and I tried to prove during class all of the properties of logarithm follow from that one definition. Um, I know that some of you haven't even thought about natural log since your pre-calculus midterm more than a year ago. So some of the homework that you probably already completed is reviewing a lot of those properties, and I'll go through some of them here. So first, just the graphical properties. You guys should know the graph of log. We drew this one in class. It's a lovely increasing concave down curve, got an asymptote at the y-axis, has an x-intercept at 1, first tensor scale, e, log of e equals 1, and e is approximately 2.718. Okay, and if you know that graph, this isn't calculus, this is still pre-calculus. How do we graph transformations? So for example, y equals minus the log of minus x. So both of those minuses are going to graphically correspond to a reflection. The minus x will be a horizontal reflection, and the minus in front of the log will be a vertical reflection. So the graph of this function, now the domain, negative x has to be positive, so x has to be negative, right? And the range is still all real numbers, but we've been vertically flipped, so the graph should look something like this. And now the x-intercept will be minus 1, and at minus e, the function will equal minus 1. And the function will equal positive 1, for example, at 1 over e, right? Negative 1 over e, which is approximately negative 1/3. So we can see it's the same shape graph, just reflected around. And again, we can do a different kind of transformation, this kind of shifting. So log of x minus 2 plus 1. So you can think about it geometrically. The minus 2 here shifts the graph to the right by 2 units, and the plus 1 shifts the graph vertically up 1 unit. We can also think about domains. X minus 2 has to be positive, so x has to be bigger than 2. So if we draw the graph, I'll have a vertical asymptote at x equals 2, and my graph will roughly look the same shape. And now I can ask, where's my x intercept going to be? Well, so because I've been vertically shifted up by 1, it should happen where the log part equals minus 1, right? So that means x minus 2 should equal 1 over e. So this is going to happen at 2 plus 1 over e, about 2 1/3. It's easier to find the point where x is 3, where x is 3, y is going to equal 1. Excuse me. How do I erase? Here we go. So we'll have the point 3 comma 1, for example. And we'll have the point 2 plus e comma 2. Okay, so at this point we have to get more number sense to deal with natural log and e as a number. First, let's look at these log rules. So the basic log rules, as we re-derived in class, are the product rule. Log of a product is the sum of the logs. and that one lends itself to the exponent rule and the quotient rule for logs. And okay, so sometimes if you get a log of a complicated expression, it's easier to break it down. So here we think about the square root as the 1/2 power. So this is the same as 1/2 log of x minus 1 over x. And we can think about that quotient and rewrite this as 1/2 the quantity log x minus 1 minus log x. And sometimes that kind of algebraic rearrangement will make it easier problem to solve. On the other hand, sometimes we want to combine logs, and if you have a sum or a difference of logs, we can take each coefficient, we can take this 3 and view it as a log of x cubed, and we can take the 2 and view it as a log of x squared, take the minus 4 also. So we can rewrite this as a single logarithm of x cubed times y squared divided by z to the 4th power. And these kinds of manipulations seem foreign the first time you see them, but hopefully it feels pretty natural, no pun intended. And we can use those kinds of manipulations plus a little bit of number sense to try and just, whenever you're doing an application problem later on, you'll want to know if your answer is reasonable, and you can do some quick approximation in your head, especially if you have a couple values, right? So we know that log of 2.718 is approximately 1 because 2.718 is approximately e, and we can take some other common numbers. If you've done half-life calculations, then you'll get used to, this is a typo, 0.693, and because 3 is just a little bit bigger than e, log of 3 is just a little bit bigger than 1, and okay, so it doesn't always work out so cleanly, but if you have a number like 0.25, that's the same as 1 over 2 squared, right, 1/4. So I could write this as, or maybe I should even say 2 to the minus 2 power. So it's minus 2 log of 2. So it's approximately minus 1.4, let's say. And log of 1 over 72, I could rewrite that as log of 72 is 9 times 8, so I can write that as 3 to the minus 2 power times 2 to the minus 3 power. So that's minus 2 log of 3 minus 3 log of 2, and that's approximately minus 2.2 minus, let's say, 2.1, so I can say it's about minus 4.3 overall. Okay, so handy skill to be able to approximate those, but we'll usually have a calculator if we really want decimal answers. Okay, now there's only one calculus fact we know, which is that the derivative of the log function, by definition almost, is 1 over x, by definition plus using fundamental theorem. And so now we can just review all of our derivative rules. If you have a composition of functions like this, we have to use the chain rule several times. So it's a log of something. So my derivative is 1 divided by the inside function times the derivative of that inside function. So I can do this as a side work. The derivative of log of x squared is 1 over x squared times, now we have a second chain, times the derivative of x squared, which is 2x. All right, so overall I get, my x's cancel, so I get 2 over x. I guess we can clean that up. 2 over x log of x squared. And we can clean this up a little further now, realize that log of x squared is the same as 2 times log of x. So we can cancel the 2's, and we can get a final answer of 1 over x times log x. Okay, so we can see that using the properties of logs can sometimes clean up or even simplify our calculus. So if I want to take a derivative of this kind of function, I don't want to use my triple chain rule plus product rule and all of that. Instead, I'll rewrite this first as 1/3 log of x minus 1 minus log of x plus 1. And now it's a really easy derivative to take. I just have still 1/3 as a constant coefficient. And then the derivative of log of x minus 1 is just 1 over x minus 1. So we can take that derivative much more easily than if we used chain rules and quotient rules. And if we have this kind of question that asks us to use the second fundamental theorem, right, we can review that. So the derivative is the integrand evaluated at the upper bound. So it's going to be log of x quantity squared plus 3. And then we have to multiply by the rate of change of the upper bound, which is just the derivative of log x, which is just 1 over x. So that's how we can take a derivative there.